Hello! In this video, we'll continue the multi-cycle data path and implement the rest of the instructions. So next, let's take a look at the store word instruction. So remember that the store word instruction will write the data from the second source register into the memory. We already have most of the capability. We can fetch the instruction, we can read the registers, but now we need to read two registers instead of just one. So we'll add a wire here from the RS field of the instruction to the register file and read out the second source, and we'll expand the register, the flop after the register file to hold both sources. Next we'll be able to take that value, we'll call it write data, and bring it back to the write data port of the memory. And on that, meanwhile, we are calculating the address to write to on the third step. And on the fourth step, we could take the address, come around here like in a load, the data from the register file, and assert the memWrite control signal to write the data into memory. So that's all we needed for store word. For R-type instructions, we actually already have all the hardware. On the first step, we fetch the instruction from the memory, put it in the instruction register. On the second step, we would read the two sources. On the third step, those sources would go to the ALU, and we could do the operation. And on the fourth step, we could take that result and write it back into the register file. So that was for R-type instructions. For branch instructions, we need to calculate the branch target address, and we also need to decide whether to take the branch. So let's draw that on here. On the first step, we would read the instruction, but we could also capture the program counter. On the second step, we can take the old program counter and add the immediate. So on the second step, we've got an immediate from the sign extender, and we could add those together and get a branch target address, store it in ALU out. On the third step, we could compare the registers. So we have A and B, put those into the ALU and do a subtract and see if they're equal. And then if they are equal, we could take that result from PC plus immediate and write it into the program counter by asserting PC write, and that way take the branch. Notice that the PC is updated in the fetch stage to PC plus 4. So since we want to do PC plus immediate, not PC plus 4 plus immediate, we needed to keep that copy of the old program counter to add the immediate to. So to summarize, here's our multi-cycle RISC-V processor. The black part is the data path. The black wires are generally, the heavy black wires are 32-bit buses. The light ones are smaller buses like the 5-bit register identifiers. And the blue is the control signals. So again, we have our architectural state, the program counter, the memory, and the register file. Then we added the sign extender to get the immediate, and the ALU to do the math. This time, we've had to add registers after each step. So to hold the values of the instruction and the data, to hold the values coming out of the ALU, out of the register file and out of the ALU, to break into steps. And we've needed additional multiplexers to choose from one of several options. And then we add the blue control signals to tell the ALUs what to do and to assert the write enables to the memories and some of these registers to capture values on the appropriate step.